Hello everyone. I want to discuss about our REU project, which is enhancing density properties if in high temperature refractory materials through additive manufacturing technique. I want to thank all of my teammates for their collaborative effort to successfully complete this project. So without further ado, let me briefly talk about what we did and what we are going to show here. So, as the name suggests, so we are concerned about two things. We want to enhance the density of an high temperature refractory materials. For this case, this will be tungsten, and the additive manufacturing technique that we're going to follow is a laser powder bed fusion. So, the idea is to involve a thorough research and look at the literatures to see what kind of approaches they did for improving the density, and amongst that we found that okay, optimizing the process parameter was the best approach for this kind of studies. So with the process optimization we went to a DOE approach, and from that we had a, I mean, the laser power and the hatch distance as our inputs, and from that we got a good surface response with good predictability, and the highest yield on density we got was 98.03%. Now let me discuss more about the background of this project. The Why tungsten? Because tungsten in additive manufacturing technique is a challenging material. Why? Because of it has a high melting point and high DVTT, and this causes the tungsten when it involves in solidifying, reheating, and remelting in laser powder bed fusion, it has a tendency to cracking, and this cracking phenomenon, this cracks and micro cracks decreases the density of the bulk sample overall. So by far it's not practical, but as we want more design complexities which are not achievable through the conventional manufacturing, yes, so to integrate both of them we need to come up with something. Numerous studies have been conducted by a lot of researchers. Each of them used several approaches, all of them, some of them mentioned here. Some of them use the process optimization technique, some of them use alloying technique, some of them use cross processing like HIP to improve on the densities. Well, these are all good approaches, but amongst this one, for this scope of research, we want to go with the process optimization because we think this goes in line with the simplistic notion of the additive manufacturing. To keep this in mind, this is the experimental setup that we followed. We went through a literature review. We found some input variables for our DOE. We performed the DOE. We did the fabrication on EOS M290 machine. And then we measured the density from the ASTM standard B962 section 23, and then again we give it to DOE and find the predictability and the the performance of our analysis. So based on the research that we have conducted, we found that they all agree the scan speed is more or less 400 millimeter per second and the layer thickness is 20 microns. So we went fixated with that one, and from the researchers we found a range for the laser power and the hatch distance to be from 300 to 350 watts and 60 to 85 micrometer respectively. With these inputs, we performed the central composite design, which was proposed in our REU project. And from that one, we fabricated 9 of these samples, and we give these feedbacks to the DOE. And as you can see in the experimental results section, we got these results by obtaining the DOE. And from the table, as we can see here, the laser power has the most effect on the density, and then the hatch distance, and then the other quadratic effects. But ignoring these ones for now, our only concern is the laser power and hatch distance. And as we can see, laser power, the lower the laser power is, the higher the density will yield. And the hatch distance has a quadratic relationship, but yes, as we can see here, we found a threshold. But based on this other researches as well, we figured out that 300 watt is a good, laser power startup. And this is like a comparative analysis of the other researchers that reported the density for tungsten with different methods, like Field et al. 97.3%, Sidambe et al. 94 to 98%, and we obtained a density 98.03%, which is really, really good compared to the other researches have been conducted, as you can see from this table. And we think that this approach that we followed is a good one, as we achieved a really good density, and we believe that integrating other in situ processes with this optimized process parameter will obviously give high yields to the density properties. That's it. Thank you for listening to us, and I want to thank to Dr. Amari for supporting us for this REU project, and I want to thank all of my teammates. Thank you.